What does it mean? Let's say you are the city government. You have a face identification model working for you. And the cop comes and tells you, oh, I have an image of a person I've taken on a Monday morning and one person on a Tuesday evening. Two different locations in the city. The first day, let's say, he was wearing a coat with a cap. On the second day, he was wearing a shirt and a pant with no cap, but there's no facial hair. Can you tell me if these are of the same, these images belong to the same person? Models developed based on triplet laws were able to predict whether the images belong to the same person or not, but then you have to give the image 1, image 2 and image 3. Image 1 being, image 1 and image 2 are images of the same person, and image 3 has to be image of a dissimilar person. You've got to give images in the correct order for the model to generalize. But many times this model did not generalize well and it was making errors. You don't want to make an error, even 5% error, 7% error in judging people, because then you may have to catch a real law-abiding citizen and put the person in prison, or let a criminal off the hook. So you have the quadruplet laws paper published, I think, as it is in the CVPR 2017 last year. It gives a very, very high accuracy rate and also generalizes well. Architecture is very similar, again, a bunch of convolutional neural network. If you have any image processing model with CNNs, the minimum to maximum number of layers will be somewhere between 6 to 10 layers. And then 1 or 2 fully connected layers, and the last layer will be a softmax layer. That's predominantly the image processing models till now. We do have image processing models like ResNet, which published by Microsoft, I think, 2017, which is around 152 layers. There are a couple of experiments where people have trained 1,000-layer CNN architecture too, but they found that it's not any more efficient or any more accurate compared to ResNet model, which is 152 layers. Yes? The reason quadruplet loss model was a lot more is the two benefits. One is, in the triplet loss, for the model during inference, you got to give the images in a correct sequence, and that was a big problem, because sometimes you don't know whether the person 1 and person 2 are same people or not, and when you give it to the model, you have to give 2 images of the same person and 1 dissimilar person, and then it becomes an issue. Number 1. Number 2, the model was not generalizing enough, in the sense it was, globally it was generalizing faster, but locally it was not generalizing. What does it mean? It means, if you have a person, normally surveillance cameras are, let's say, 10, 15 feet above the ground, and they're taking a picture from above. So you will normally have a view from on the top. Let's say if you wear a cap, the view of the camera is very, very less. So the number of pixels on a face, on the body, are less number of pixels the model has access to make a prediction. You actually have the size of the person, maybe the length and the width, and also the gait, the position, the size, the other details of the person. You can't rely on the dress, because people change the dress over a period of time, or you can't even rely the hair on the body, because people, if someone wants to really confuse the model, they can change the hairstyle and then confuse the model. So it was not generalizing at the local level, it was generalizing fast enough at the global level. So from the face it can detect, but if there is a minor change in the beard or the mustache or something on the face or on the body, then the model was, the accuracy rates were dropping. That's the reason why I think they went from triplet loss to a quadruplet loss.
But is it possible for the triplet loss, if you give in a sequence, say 1 to 3 pictures, then 3, 1, 2, 3, 2, 1, just to average somehow and find a better solution?
If you can do that. The only problem is then if you know the answer, then you can test the model. But imagine in an inference time, let's say the model is sitting on a surveillance camera and you are in the police control room, and you want to find out whether this person is the same as this person. You are asking the model will make a prediction, and based on the prediction, you got to take an action. And if the model's accuracy rate is, let's say, 95%, so 5% of the time model is making a wrong judgment. And do you want to take an action or not take an action based on this? Because if you arrest a person wrongly, then you have a legal and public relations and media issue. And if you don't take an action, and that happens to be a criminal, the person actually will be going away. So the problem is, so no AI model will be 100% accurate, because I would be very surprised as an AI scientist if someone says mine is 100% accurate, it's a problem. 95% I think is an acceptable number, 98% is an acceptable number. Beyond that is going to be difficult. In this scenario where for a triplicate loss, for a model to come up to 95% accuracy, it only, if you have to give the image in certain sequence. So let me explain this, when I say sequence, what it means. When you're training a model, you have to tell the model, image 1, 2, and 3. 1 and 2 are of the same person, 3 is of a different person. And it starts understanding, finding the similarity between 1 and 2 and the dissimilarity with the third, and then starts understanding. During inference, you have to still give 3 images. Third image is easy, you can pick some random image. How do you know image 1 and 2 are the same person? So let's do a little bit of a logical argument. Let's say you did find the same person in 2 different cameras, and you give it to the model. The model will say, yeah, it's the same person. But you did not know. And there were 3 different people. Image 1 is person 1, image 2 is person 2, and image 3 is person 3. And model gets completely confused. It says, oh, they're not the same people. But you don't know that, because it's the inference time. That's a big problem in image processing models, especially in smart cities, especially in the legal scenarios. When you train a model, even 2%, 3% of inaccuracies can really make a big problem. So this actually brought down the variation in the inaccuracy. For example, if you give in any sequence, the model was still consistently performing 93 or 95% accuracy, which was actually a good idea. Because in the triplicate loss, if the accuracy rates varies between 80 to 90, then you don't know how much of error you're making in the system. This is another paper which actually called sphere face. In face re-identification, there are 2 types of scenarios. If the city government already has images of some people, for example, I don't know whether this is reality or not, let's say Facebook agrees to share information with the city of the 500,000 people in Vienna. It knows who the people are because you know the names of the people and you have the pictures. And you have some other people whose names are not there on Facebook, or it's not being shared, or maybe tourists or whatever. So you have the controlled group and the non-controlled group. This paper was published, or this situation addresses, you have a closed set face recognition, you have an open set face recognition. A closed set is the images of people or faces of people are known to the model. And in this case, if you don't know the images of the person, then you would find out that the person belongs to the not. This is the same use case as I mentioned earlier, but I think the accuracy of this model is very high. If you look into many of the models that came before the other, this model was of higher accuracy, 99.42. Actually, 99.42 itself is a difficult thing for me to believe, but also while they do this, the number of data points it's consuming is quite less. So if you want to implement any face recognition solution, you may want to consider this paper. If you have a surveillance camera, and if there is a remember the first paper I showed, if you have 10,000 hours of video coming in every hour, you can't have all of this video stored, so you want to process some. For example, there is a camera on the street, and if there is an anomaly or there is a crime happening in the street or there is a traffic accident, only then the model has to take the video, maybe 5 minutes before or 5 minutes after, and store it, but all other video it can discard. So instead of storing hours and hours of video, you can only store only a few minutes of video, which is required. That means the model has to be sitting on that camera and deciding the actions. It should look for a crime action or a criminal action. It should look for a traffic accident. So in this model, you can have parallel CNN architectures which can detect human action. Before deep learning really picked up, classifying actions in video had a lot of handcrafting. That is the optical flow. Let's say a person is running in a video. So if you look at frame 1 to frame 100 in a video of 10 seconds, frame 1 to 2, 2 to 3, 3 to 4, you see a person moving slowly, the legs and the hands, and then from frame 1 to frame 100, by the time you reach there, you know the person is running. So you actually have to look at each of those 100 frames and detect collectively these 100 frames reflect a human action called running. And that's called optical flow, how the flow of optical in the image was handcrafted. But this is the first paper, I think, which actually lets you not do any handcrafting of optical flow. So there are two image sequences. You actually have the motion net, which actually just detects the motion of an object from frame to frame, and that is fed into a temporal stream. If there is a motion of, let's say, a person walking, and that happens over a period of, let's say, 100 frames or 1,000 frames, and that is fed here. And there is another simultaneously trained CNN architecture which actually can detect optical flow. This entire model is trained end to end. So the model over a period of time understands to detect the spatial stream and also the motion stream. This is I think, the first of its kind in terms of detecting the optical flow and the action movement without any handcrafting. And this model, I think, also does inference very, very fast. I think it's around 200 frames per second. So it can do a live detection of any event happening. But the interesting part is, if you look into the size of the architecture, lots of convolutional layers here and fully connected layers. And FC6 and FC7 are fully connected layers 6, 7, and 8. Any questions? A long time ago, when I was about to teach in a university, I asked a professor, how do I know the students are really understanding what I'm talking? How do I know they're really enjoying what I'm talking? He said, okay, watch for the facial expressions. If they are really engaged, maybe they're making notes or writing or typing in the laptops, and once in a while they see smiles on their face. And when you walk up and down, they're looking at you and their eyes are tracking. But if the laptops are down and they're leaning back, and even though they train their eyes to walk with you wherever you go, there's no facial change in the facial expression. That's not even a smile. That's when you should stop. So, should I stop? Should I keep talking?
You must.
Sorry?
You must.
I must. Thank you. Yes, sir. You had a comment.
Maybe you could change focus a little bit, because this is sort of a utopia of various networks. So a lot of people in the audience know about networks, but I guess what I was expecting from this talk was the case study of how a city can engage you to actually make the city work better. So these are there are lots of examples of networks, but not really a description of European city living with GDPR, using techniques like this to actually make the city work better.
Yeah,
Give us an
yeah.
example of that?
I don't have an example of that. I'm sorry if you were expecting something different. I was planning to talk, what I'm planning today was trying to explain some of the use cases in a smart city context and how do we solve using artificial intelligence, especially deep learning. If I take the example of a specific city and how they're solved, I'm not prepared for that today, but if I have to explain that, I will have to actually pick use cases how they're solving. Many of the smart cities use cases, which I showed in my first slide, these are predominantly the use cases almost many smart cities start working on. For example, in the United States, some of the cities, the first use case they want to solve is how do we answer the questions the citizens have about taxes or about the basic facilities or trash picking up or whatever. So they implement a chatbot. The most common, the first implemented use case in any smart city is chatbot. So you actually have a website, go there, click on the chatbot and start typing your questions, you get answers for it. That's one of the first things. And second, of course, is maybe some little more advanced solutions like how much property tax do I owe? Can I get a waiver for my traffic violation or ticket I got? These are some of the next things I've seen happen. If you go to some of the Chinese and Asian cities, some of the smart city solutions are focusing on preventing crime. So detecting anomalies, for example, if there's any crime happening in the city, or a traffic accident, or traffic congestion, or unexpected cars, let's say unauthorized cars on certain streets or certain roads when they're not supposed to be doing. So all of these actually happen to be image processing models. So what I'm trying to do today is actually pick a few of the most common and also a little complicated use cases in a smart city where you can use images to process information. There are some use cases where you don't need images, you just need temporal data or certain other data to process and find out what's happening, but I'm focusing today on that. And in 45 minutes, that's what I picked, and I'm sorry if I put it, it was not matching what you were expecting. But this is what I was planning to do today. Another smart city use case is people use their smart devices to take videos of scenarios and start uploading on the social media. Even though cities have their own infrastructure of surveillance cameras and other things, the power of individual citizens taking pictures or videos and uploading onto social media is unimaginable. You can actually tap into that information available and process it and make sense of it. For example, this is a paper published which actually can track an event that's happening live, even in the situations where there are no surveillance cameras. The city does not have surveillance cameras on the street, but there is a crime happening, or there is some event happening. They tracked I think a procession going on, and then they designed a system. And this is very similar to the implementation solution is very similar to what we have done, what papers in the previous one. But if you have a large-scale mapping of videos where you have the live information being processed and you can detect what's happening. All of these smart city solutions is more, it's a little more difficult because of the infrastructural needs. If you look into sensors that's creating data is not just your smartwatches or smartphones and surveillance cameras and so many other sensors. The amount of data that's coming in is unimaginable, and having a proper infrastructure is not that easy too. If you look into, let's say, the city traffic lights and maybe your smartwatches and stuff that's being, the data coming in, if you want to store it on the cloud, this is a paper published in 2017, which talks about have some sort of load balancer so they have multiple servers receiving the data and storing it. So you have, let's say, n number of servers which collect the information, and all of this information maybe will come into one master server, which could be stored. Some of the information can be stored for future, or some can be immediately processed for quick action. And there is also a storage stream which is done not just for the post-processing, but also sharing the information for third-party organizations. Let's say you have taken the videos, or if you've taken the images of a specific location, you can also share that information with any social media or the traffic or a taxi companies for APIs. There's another paper I want to share before I end is the online data processing difficulty. If you have not just the numeric data that's coming in, also you have image processing data that's coming in, plus the NLP and the text information coming in. People are texting, and then you're trying to get the message out of that too. This is an architecture which was published a year ago, which gives insights into how to collect the data, the numeric, text and image, pre-process the data, and make the data available for any AI solutions you can develop for smart cities. That's all I have for today. Any questions, please?
Where do you see the cost of complicating well, whether text economics worldwide? Where do you see the cost of complicating, especially if just Asia, Europe, America?
Deep learning, the question is which part of the world the fastest uptake on the smart city type of use cases being deployed. In my opinion, using image processing, I think China is one of the few countries really, really advanced, where you have production systems available as of today, comparable to no other country that is really advanced. But there are certain cities in